Okay, welcome back everyone. Moving into chapter 4 in our textbook. The primary topic here for chapter 4 could probably be considered as being solutions. So we want to start to look at the molecules, compounds we've been discussing so far, and even the reactions we've been talking about in the previous chapter, and start to look at what might happen if these were dissolved. Generally, we can use water as a solvent to dissolve a lot of chemicals, but the material we dissolve, the liquid we dissolve a compound in could be anything, any other chemical component. So the first thing that we really need to consider if we start to think about making a solution or dissolving a solid or a gas or even another liquid in an additional liquid is the concentration of that solution. How much of the dissolved material is present compared to or related to how much of the liquid that we dissolve it in is present. So I've got the definition of concentration here on the lecture notes. This is the amount of solute dissolved in a given quantity of solvent or quantity of solution. There's a couple terms in there that we should focus in on a little bit because you should understand what they're describing. The solute is the term we would use for whatever is being dissolved. So if we're making a solution, say, of salt water, the solute would be the sodium chloride solid that is going to dissolve in the water. The solvent generally is the material that the solute is being dissolved in. Usually the solvent is present in a greater quantity, although that's not necessarily the case. Often water is considered the solvent even if it's there just a little bit. So you could have something like 95% sulfuric acid, with 95% of it by mass is sulfuric acid, only 5% of it by mass is water, but you would still consider that an aqueous solution of sulfuric acid, and water would generally be thought of as your solvent. So in the example of sodium chloride, water would be the solvent. Okay. Now, we want to get a handle on, right, what's the quantity of solute relative to the quantity of solvent, or maybe the quantity of the entire solution that is created. By far, the most common way to do that in terms of chemistry calculations relates to moles and is called molarity. Now, the symbol for molarity is a capital M. And that's an important thing to keep in mind because you'll see that capital M, but you really need to recognize that capital M actually involves two sets of units. Because the definition for molarity is how many moles of solute there are divided by how many liters of the entire solution there are in a solution that we make. So this is nice chemistry-wise because moles, of course, we can relate to a chemical reaction or a balanced chemical equation, right? And liters is our standard unit of volume from the SI units or from the metric system. And this can be a little tricky. You have to realize when you see that capital M, this is what it means. It's comparing these two units. A lot of times people will make the mistake of thinking the capital M just means moles. And it doesn't. It means how many moles are present in a certain amount of liquid. If that liquid happened to be a liter, then that would be how many moles are in there, right? But it's pretty rare that you do an experiment on an entire liter of solution. Okay, now, this is our measure of concentration, molarity. We want to look at how this will kind of fall into calculations. So here's an example. We want to calculate the molarity of a solution that contains 0.0250 moles of ammonium chloride in exactly 500 milliliters of solution. So right there, those are the two pieces that we want, according to this definition we have just above, moles of solute per liter of solution. So similar to what we saw with density, right? We're not going to be canceling out units in this particular problem, but we need to be comparing them in the right way. Although we will have to cancel here because we'll have to change that to liters. But to calculate the molarity here, we want moles of the solute, and we want to divide by liters of the solution. Right? We're given moles of the solute, 0.0250 moles of the ammonium chloride. That's our solute that's dissolving in the water. Now, if we make exactly 500 milliliters of solution, we want that to be in liters if we're going to plug it into molarity here. So let me do that conversion. 500 milliliters, 1 liter is equivalent to 1,000 milliliters. That would be 0.500 milliliters. Now, sig figs are a little weird in the way this problem is written. It says exactly 500 milliliters. That means this volume shouldn't limit our significant figures. So we're going to be limited to the 3 from here. So I just kept 3 in my calculation here. And I wrote milliliters. That should just be liters now because we canceled out milliliters. That's how many liters this total solution is. So that is what could go here in the denominator of that fraction. Right now we've got moles over liters. That's the set of units that describes molarity. We just need to divide here. So we'll have to find the calculator. 0.025 divided by 0.5. Actually, that's not that hard of a division. 0.05. And 3 significant figures, so let's keep 2 more zeros there. And moles per liter, right, is equivalent here. Those are the units, but you may want to write this in your final answer just with that capital M for molarity. So remember, those two are interchangeable, and we certainly want to be able to, when we see the capital M, recognize the 2 sets of units there. Okay, let's look at another example here. How many moles of HNO3? So HNO3 is nitric acid. We haven't really discussed naming acids. We'll get to that a little bit later. How many moles of nitric acid are present in 50 milliliters of a 2.50 capital M there? That's usually read as molar. So a 2.50 molar solution of nitric acid. Now, in this case, let's think about what we're looking for. We want to get to moles. We've got a volume here in milliliters, and then we've got the molarity. Here's where recognizing that this capital M means 2 units is going to be helpful, because 2 units in a fractional relationship, that's what we have called a conversion factor. Right? So this is a problem we can use dimensional analysis or just working our way through the units to figure out. So let me start out with the 50 milliliters. We've got 50 milliliters of this solution. What we want to do is work our way to moles. Well, moles is part of the molarity here. Remember, this capital M really means moles per liter. So if I can get to liters in my calculation, I could cancel it with the liters that's part of molarity, and that would get me to moles. So starting with 50 milliliters of solution, I might want to change that to liters. And again, in the SI units or the metric system, 1 liter is equal to 1,000 milliliters, right? And let's keep solution in there just so we keep track of what we're describing, right? Now, 2.50 molar means 2.50 moles of the solute, which is the HNO3 or nitric acid, per liter of the solution. So multiplying by the molarity here, 2.50 moles of HNO3 per liter of the solution. That will cancel out the liter units that we still had hanging around there, and that will give us what we're looking for. How many moles of nitric acid are in that particular solution? So 50 divided by 1,000 times 2.5, and we had 3 significant figures, a couple places here, the concentration and the volume we started with. 0.125 moles of nitric acid would be in that solution. Okay, we've come to the end of a page. That's probably a reasonable place to stop the first video. We'll pick up on the second page of the lecture notes.